To kick things off by doing an example, we're going to compute a Laplace transformation. And in this case, went ahead and took the liberty of working out a very simple example that would be typically expected in your homework and in your final exam. Okay. And in this example, we're computing the Laplace transform of a function that is equal to the number 1. Okay. So first of all, notice that the function of t is set equal to 1 from observing what is within the braces here. Afterwards, using the definition of a Laplace transformation, we can see that the Laplace transform of 1 is equal to the improper integral from 0 to infinity, e to the minus st times 1, or f of t. And that is taken straight from our definition, which then just simplifies to the expression you see down below. Now, you may have noticed that this expression here is actually very similar to the expression that we solved previously up above. You will notice that instead of e to the ct, we have e to the minus st. So if we let c equal to negative s, then from before, the solution we obtained from the last improper integral was negative 1 over c. So we can let negative s equal to c, plugging it in, and solve. So therefore, we can say that the improper integral from 0 to infinity of e to the minus st dt is equal to the Laplace transform of 1, which is simply 1 over s. And this is something you would find in a transform table, a Laplace transform table. And there's another condition here that has to be emphasized. Number 1, s can't be 0, otherwise the expression is undefined. Number 2, s can't be negative, otherwise it does not converge. The limit will not converge. So it must be bigger than 0 in order for the limit to converge. Okay. So that's the other aspect of Laplace transforms that have to be carefully understood. And for more advanced Laplace transformations, you would have to resort to some calculus tricks, like the root test or the integral test, to assess whether or not convergence or divergence was taking place with the limit you were using. Okay. So that's a simple example. Let's do one that's slightly more complicated, but not all that much more difficult. We're going to do this example here. We're going to compute the following. Compute the Laplace transformation of e to the a times t. Okay, so that's our next task. So let's go ahead and proceed. We're going to plug this in again, just like we did before. So Laplace transformation of e to the at. Okay, and this is going to be set equal to the integral 0 to infinity e to the minus st, that's from the definition, multiplied by the contents within the Laplace transformation. So that's what goes here. That's going to be e to the a times t. Okay, and this can be simplified a bit. This is going to be equal to the integral from 0 to infinity, okay, of e parentheses a minus s times t dt. Okay. Now you might have noticed again, this has the form that we saw before with e to the ct, right? If I scroll up a bit again, you'll notice again it has this form, e to the ct. That's convenient because we know what the solution was for that, right? So again, we can say, okay, let's let c be equal to a minus s. Okay. So the solution before was minus 1 over c. So again, minus 1 over c will be set equal to minus 1 over a minus s. Okay. And if we simplify this a bit, this is equal to 1 over s minus a. And again, you'll find this in your Laplace transformation table. So to officially say what this all equals, we would say Laplace transform of e to the at, okay, is equal to 1 over s minus a, provided something is very important here, provided that s is bigger than a, and that allows for convergence to take place. It also prevents the denominator from being undefined. Okay. Now we have one more example I want to show you guys, which is a bit more involved, and I want to make sure I reserve an entire section of the video for that as well. So stay tuned. This is about as complex or involved as a Laplace transform can be in the next video.